This video introduces priority queue abstract data type. It shows a very efficient implementation of priority queues, which is going to be binary heap. Also, it introduces heap sort, which uses binary heap to sort a sequence of comparable objects. Here's the outline of my next lecture. First, I will introduce priority queue abstract data types. Then I'll talk about the very simple implementation of priority queue, which is binary heap. I'll show you both the structural property and min or max heap property of binary heaps. Then I'll talk about insert and delete min or max, which are the two major operations that you can do on a binary heap. Then I'll show you the Java implementation of a binary heap. Then after that, I'll explain how heap sort can be implemented using a binary heap. And finally, I'm going to compare heap sort with other sorts. Let's begin by introducing what a priority queue is. It is basically a data structure that allows the following two operations. One is insert, which adds an element to the queue, and one is called delete min, which finds the minimum element. Sometimes it's delete max, but min or max, they're both going to be similar data structures. You can convert one to the other. But I'm going to go with delete min here. Delete min finds the minimum element in the queue, removes it from the queue, and returns it as the return value of the operation. Now, why do we call this priority queue? Because it is very similar to the normal queue. In a normal queue, you have insert or enqueue and delete or dequeue. Here we have like similar operation, insert and delete min. The only difference is in a normal queue, we had a first in, first out policy, which you always have to remove the element that was inserted first. But for the priority queue, there is no first in, first out anymore, first in, first out anymore. Basically, we have whoever has the lowest priority, or in some case, we say whoever has the highest priority has to be removed first. Now that we know what the priority queue is, let's find out how we can implement it. There are three implementations that I'm going to explain in this slide. None of them are good enough, and I'm going to explain them one by one. First one is to keep all the elements in the priority queue in any order we want. We just place them at the end of an array, and we always implement the insert operation by appending to the list. So let's say you have these elements 10, 51, 6, 8, 7, all the way to 12. They are inserted in the same way that we see them coming. So first we insert 10, then 51, then 6, then 8. It makes the insertion very fast. It's going to be order of one insertion operation. The problem is for min deletion, you got to spend order of n to find and remove the minimum. Why? Because when you have an unordered list of elements, to find the minimum, the only choice you have is to traverse the whole array from left to right to find the minimum value, and then when you remove the minimum, in this case -3, there will be a gap in the array. Then you need to fill the gap by shifting every element stored after the minimum one cell to the left. So this operation is going to be extremely time consuming. The order would be order of n. The other implementation is kind of similar. It says keep the element in an ordered list. For example, if you consider the same sequence of elements that I mentioned earlier, if you insert them, the insertion takes a lot of time. The insertion will be order of n because you have to always insert the elements in a way that the array remains sorted, but the minimum deletion wouldn't be that difficult. You just remove the minimum. The minimum would be the first element. Right? This operation or this implementation has a very fast min deletion because the minimum is always in one end, or if you can say we have a max priority queue, then the max deletion would be very fast because you always have the maximum in one end. But the problem is that the insertion will be time consuming because every insertion should not change the sorted property of the array. So that makes the insertion very inefficient and impractical. But the mean deletion would be fairly simple. The third choice for implementing a priority queue is to use a binary search tree. A binary search tree is a very interesting data structure. We use it to store a set, but you can also use it to store a priority queue. There's no problem with that. It's going to have an order of log n insertion, as you know, because the cost of insertion is the cost of the height, is the length of the height of the tree. If you use a red-black tree or AVL tree or any tree that does self-balancing on the binary search tree, you can get always order of log n, but if you don't do it, the average time complexity for insertion would be log n because the height would be log n on average. But the mean deletion also would be similar to the insertion in terms of complexity, because to delete a mean, you need to find the leftmost node. The cost of mean deletion in the binary search tree would be the order of the height. The height on average would be log n. So again, we're going to have a pretty fast mean deletion as well. If you want to do delete the max for a max binary priority queue, then you need to delete the rightmost node with the same complexity log n. So binary search tree would be a great solution for priority queue, but it's a very complicated data structure for fairly simple priority queue. Priority queue is a very simple abstract data type and doesn't need that much complexity that comes with the implementation of a binary search tree, especially if you want to keep it balanced. A lot of rotation happens when you're doing insert and delete, and it's too much complexity that comes with a binary search tree that we try to avoid it when implementing a very simple priority queue abstract data type. In the following slide, I'll show you the simplest way to implement a priority queue, which is going to be using a heap. In this case, in this video, I'll only focus on binary heap. Now let's find out what a binary heap is and why we consider it as the best implementation for priority queue abstract data type. A binary heap is a binary tree which has a very interesting structural property. It is a complete binary tree. What does complete means? It means it's completely filled except for the last level, the bottom level. As you see, the first level is A, it's completely full. The second level is BC, it's completely full. Then we have D, F, G, it's completely full. The last level is not full. And also the bottom level is filled from left to right. So we have H, I, J in the leftmost part of the bottom level. If I add an extra element, let's say after J we have H, then it becomes the right child of E. If I add another, after J we had H, I, J, K, K becomes the right child of E. If I add another element, let's say after K in the alphabet we have L, becomes the left child of F, then M becomes the right child of F, then the rest becomes, the children of G, and that's how you complete the bottom level. It can be stored in a linear array. That's why we like a binary heap, because it's not as complex as a binary search tree. In a binary search tree, the implementation was complex because every node has to keep track of its left child and right child. So every node has to store 2 pointers to the 2 children it can have at most. But here for a binary heap, because it has a structural property that I mentioned, it's a complete binary tree, you don't need to store the elements of a binary heap in a sequence or in a set of binary nodes. Instead, all you need to do is to store them in a normal array. As you see, A, B, C, D, E, F, G, H, I, J are all stored in a normal array, in a linear array. How is it possible? We're going to first place the root in the index 1. I kept index 0 for a purpose. I'll tell you later why. Then I'm going to place the next level B and C in the following two indices 2 and 3. Then D, E, F, G, the third level will be stored next. Then the final level H, I, J. Now if I have more elements, as I said, K, L, M, they go in the following cells of the array. Why this is a great idea? First of all, I'm going to tell you why I removed I left the first index empty. But why is this a great idea? Because the parent-child relationship will be predictable when you're using this setting and store the elements of a binary tree in a normal array in the order that I mentioned. This order is called the BFS, breadth first search. And this order allows us to create a nice relationship between a parent and child indices. I'm going to tell you what the relationship is. If the parent, let's say, consider A as the parent, right? Parent index is 1 because A's index is 1, right? And the children of A would be B and C. The indices would be 2 and 3. Let me give you another example. If C is a parent, the index of C is 3. The children's indices would be F and G, which are 6 and 7, right? Another example is D. If D is the parent, D's index is 4. The children's indices F and which are H and I would be 8 and 9, right? If the parent is E with index 5, the children's gonna be 10 and 11. It only has one child, which is J. There's no right child. If there was a right child, it would be stored in index 11. So you can guess the relationship between this column and this column. As you see, if the parent is P, the index of children would be 2P and 2P plus 1, right? The left child would have an even index, the right child would have an odd index. So left child's index is 2 times P, right child index is 2 times P plus 1. And vice versa. If you know the index of the child as, let's say, C, then the parent index would be C over 2 or C shifted to the right by 1 bit. That's how you divide by 2 in a nice way using bitwise operations. So because the indices of the array can tell you the parent-child relationship, there is absolutely no need to use a binary node, which was a complex data structure, keeps track of the left and right child. So that's why binary heap can be implemented a lot faster and a lot more efficient compared to binary search tree. That's why we're gonna avoid using binary search tree for implementing a priority queue, because priority queue is not as complex as a set abstract data structure. So we don't need to use the complex binary search tree. Instead, we use this nice binary heap, which is a complete binary tree and can be stored in a normal array without any class like binary node, which refers to the left and right child using reference. So the reason, let me go back to the final point I want to make here. The reason I kept the index 0 empty is because when you keep it empty, then the parent index can be obtained using the child index by doing a shift to the right operation, which is division by 2. And this is faster than when this index was not empty. In that case, the parent index formula would be C minus 1 over 2, which takes longer to be calculated compared to just C divided by 2 or C shifted to the right by 1 bit. So the reason we keep the index 0 empty is very, very deep. You don't need to be worried about that. But just remember, index 0 normally normally remains empty when you're implementing a binary heap. Just to practice the property of binary heap structure, which is a complete tree, let's see some examples. Is this a complete binary tree? The answer is yes, because all the elements all the tree levels are full, and you can store the elements in an array without any gap, right? A, B, C, D, E, F, G. Is this a complete tree? The answer is yes, because again, you can store all the elements in a linear array without any gap. Is this a binary tree, a complete binary tree? The answer is no, because if you want to use the formula I told you in the previous slide to place all the elements in a single array, there will be two empty cells. These two red cells are empty. So it's not, there's a gap in the linear representation, so it's not a complete binary tree. Same for this. This is a complete binary tree, and the array representation has no gap. This one is a complete binary tree, and its implementation is, linear representation is not, does not contain gaps. This one is not a complete binary tree, and therefore its linear representation does contain a gap. Please remember that this property of binary heap, which is a complete binary tree, allows us to always have a balanced tree. And having a balanced tree is important because the height is always a logarithmic function of the number of nodes. In this case, for example, in this shape, you have 225 nodes and the height is 7. The formula, the relationship between height and number of nodes is always this. The number of nodes is between 2 to the power of h and 2 to the power of h plus 1 minus 1. That makes the height equal to the log of n. You need to round always down, so it's the floor of log of n. So for this case, when you have 225 nodes, the height would be floor of log of 225, which is going to be equal to 7. Now that we understand the structural property of a binary heap, let's see the second and final property of a binary heap. This property is called the max heap property or min heap property. Depends on what type of heap you want to create. If you want to create a max binary heap, which extracts always the maximum for the dequeue operation, then you need to focus on the max heap property. Otherwise, if you want to do min heap property to extract the minimum on a min priority queue, then you need to focus on the min heap property. Here is the max heap property. The parent key or the parent node should have a greater key compared to the children, greater or equal, right? So in this case, as an example, you have a heap of size 7, so it's a complete binary heap with 7 nodes. The 3 levels are all full, and on the top you have 50, which is the key of the parent or the root, which is greater than the than both keys of the left and right children. 50 is greater than 30 and 20. Then 30 has a greater key compared to 15 and 10, which are the children of 30. And then 20 has a greater key compared to the children, which are 8 and 6. I'm sorry, 6 and 18. Yeah, I was right, 8 and 16. So please note that there is no relationship between the two children. Sometimes left child is greater than right child. Sometimes right child is greater than left child. So the siblings have no meaningful relationship. The only relationship that exists is between the parent and the children. That's the big difference between a binary heap and a binary stairs tree. The min heap property is the opposite. The parent should have less value compared to both children. So, for example, 10 here is the lowest key, so that should be on the root. Then the 30 and 20 are the children of 10, which are both greater than 10. Here I have 35 and 40 as the children of 30, which are greater than 30, which is correct. 32 and 25 are children of 20. They both are greater than 20, so that's correct. So this is basically a min heap. The left side was a max heap, the right side is a min heap. Both min heap and a max heap should both satisfy the structural property of a binary heap, which means the tree should be a complete binary tree. Now that I introduced both structural property and min and max heap property of a binary heap, I'm going to show you the two operations that a heap needs to implement. One is delete minimum or extracting the root or extracting the maximum, depending on what type of heap you have. And the second operation would be insert. So from this slide forward, I'm going to only focus on the max heap. So the extract root operation becomes the extract max operation. Let's see how the extract max is possible. Imagine you have a binary heap like this. This is a max heap, and I'm going to extract the roots. I'm going to remove the maximum value. Maximum value is always at the root because of the way we define the max heap property. So when you want to remove the 50, how the heap will look like after extracting the root. I'm going to show you step by step. The first step is to swap the first and last element of the heap. So as you know that the heap is stored in a linear array, I should say. So we're going to swap the 50 and 8. The last element would be the last node in the last level. That should be swapped with the root, right? The next step is to basically fix the max heap property of the tree. When you swap 8 and 50, you're going to get rid of 50, and the rest, the remaining part would be your tree, but it would be your binary heap tree, it's a binary heap, but the problem is it doesn't satisfy the max heap property. Why not? Because 8, which is the root, is not going to be greater than the two children, 30 and 20. So in order to fix this, we're going to apply an operation called heapify or percolate down. Heapify, which is a more common term for this operation, or in the book it says percolate down, is done in the following way. We're going to replace the root, in this case 8, with the largest child, whoever child is larger, which is going to be 30, right? Because 30 is greater than 20. So we're going to swap parent with its largest child, so 8 and 30 will be swapped. The next step, 30 is now the root, but still we have problem because 8 is not greater than its two children. We're going to do the same thing. We're going to find the greatest child of 8, and we're going to swap 8 with it. So that means you're going to swap 8 and 15, and now this is the final step. This is the final state of the max heap. As you see, it has both the structure property in place, and also it has the max heap property in place. Everything I say will be correct for the min heap. All you need to do is replace the greater with less and replace less with greater. It would be exactly the same, just you need to change the direction of the comparisons. The next operation of a max heap would be insertion. The insertion will create a state in the heap that is not following the max heap property. Therefore, we need an operation called percolate up. This is different than percolate down, but that we did for the extract max. So let's see the details of insertion operation. Imagine your heap looks like this. So I have 50 on the root, which is the maximum element, and then I have 30, 20 in the children, 15, 10, 8, and 16 in the next level, and that's it. So I have 7 elements in the heap. Then I'm going to insert a new element. Just for the sake of argument, let's say you want to insert 60, which is the greatest so far, right? In order to satisfy the structure property, which is a complete binary tree, you're going to place 60 on the last level, and it should go to the leftmost location, right? So it should be a left child of 60, left child of 15, I'm sorry. Now, although the structural property is preserved, it is not a binary heap, it's not a max heap, because 60 is greater than its child, right? I'm sorry, it's greater than its parent, right? So, however, the parent should always be greater than the children in a max binary heap. In order to fix that, we're going to use we're going to apply an operation on our heap, which is called percolate up, right? Or sometimes they call it heapify up, right? The other one was heapify or heapify down. This one is heapify up or percolate up. Let's find out how this operation looks like. You're going to compare the node 60 with its parent, which is 15, and if it is not greater, you need to swap it with the parent. In this case, 60 is not great. I'm sorry. If it's not less, you need to swap it with the parent. In this case, 60 is not less than 15. So, although we have a complete binary tree because of this relation, 60 is not less than 15, we have to apply a percolate up. So we're going to swap 60 and 15. So we're going to swap the parent and child. So 60 will be placed on index 4, and 50 will go to, 15 is going to index 8. As you may remember, the parent and child indices have an interesting relationship. The parent is always half of the child index. So index of parent was 4, index of child was 8. We swapped the index 4 and 8. Next, we're going to compare 60 with its parent. 60 is not less than its parent, 30, so we still need to continue the percolate up operation, and we need to swap 60 and 30, or I should say index 2 and index 4. Then we're going to compare 60 with its parent. Still, 60 is not less than the parent, which is 50, so we need to do this one more time. In the final step of percolating up, we compared 50 and 60 because 60 was greater than 50. We have to swap them. So now 60 becomes a new root, and we have swapped the index 2 and 1. Now 60 is the root, 50 is the left child, and the rest are placed in the same way that we had it before. This is called the insertion operation. Insertion is now completed. 60 is the new root because 60 has the highest value. Now you can check whether you have a binary tree or not. It is a complete binary tree and it satisfies the max heap property. Therefore, it's a max binary tree, or a max binary heap, I should say. The operation takes you log of n when n is the number of elements, because the number of times that you did compare every node with its parent in the percolate up was equal to the height of the tree. The height of the tree is always log of the number of elements in it, because binary heap is a complete binary tree, and therefore it is always balanced, and because it's balanced, the height is always log of n. So the operation the insert operation takes you log of n, just like min deletes or max deletes or extract max, I should say. The extract root or extract max operation also takes you order of height, and height is log n, so it's always logarithmic. Both insertion and delete operation in a binary heap would be logarithmic, would be log of n, right? So just remember that in mind. That's why we like binary heap, because it is efficient. Both insert and delete min or delete max is an efficient operation which is taking only logarithmic time. Now that we understand what a max binary heap is, let's look at the Java implementation of it. Here is the class called binary heap with a generic type T, which extends comparable of any type, which is a super type of T. And that basically means you can create a binary heap for storing a priority queue of any type you want, integer, string, double, any type, as long as it is comparable. What does it have inside it? It has a private instance field comparable array called data, and then it has an integer size which is initialized to 0, because originally you have nothing in it in the array. And then I have two constructors here. One is very simple. It creates a new array of comparables with a capacity equal to capacity, which is the input parameter of the constructor. The other one is more complex. It basically gets an array of comparables, and it uses that array to fill the binary heap with all the elements stored in the array. This one, which I'll explain later when I talk about heap sort, first sets the data equal to the same array. Initialize the size to be equal to the length of the data minus 1 because, as I said, the very first index is empty. So the length of array is 1 more than the size. Then in this for loop, it starts percolating down from the deepest internal node all the way to the root. And after it finishes its operation, you have a binary heap with all the elements stored in the data, which was the input parameter of the constructor. I'll go over this one more time and I'll talk about build heap operation for the heap sort. The size is a public getter for the size private instance field. Next, I'm going to talk about percolate down, which is the main operation when you want to delete the root. When you want to delete the root, you replace it with the last node, and then the last node becomes the root, but that's not going to be good enough for the max heap because it doesn't satisfy the max heap property because the root should be greater than the two children, but it's not most likely when you're doing this delete operation. So we need to fix the max heap property by doing a percolate down. The percolate down means comparing every node with its children and replace it by the maximum child. So this is exactly what I'm going to do. When you want to percolate down the whatever index you want, in this case we're going to percolate down the root, but it can be any other index. Root's index is 1, but it can be any other index. Sometimes you don't want to percolate down the root, you want to percolate down a node which is not a root, and you want to only fix the max heap property on a small subtree. This happens for the build heap operation. I'll explain that later. You basically find the left and right child of the given index. I assume it's root, so we're going to find out the left child index and right child index of the root. So left child will be root times 2, right child will be left child plus 1. These are the indices of the two children of the root. Then I have specified the max temporary variable that's going to keep track of the maximum elements among the left and right and parent nodes. How do you fill up the max? You need to first compare the left child with the root or the parent. If the parent is less than the left child, the max would be the left child, otherwise the max would be the root. Then you're going to compare the maximum of left and right, left and parent with the right child. If the maximum is less than the right child, then max will be the right child. Otherwise, max remains as whatever it was before. Now, long story short, line 28, the max is the maximum of left, right, and the parent. If the max is not root, which means if you need to swap the current node with the maximum of the two children, then you're going to do the swap operation. These 3 lines is going to swap the root with the maximum child. As you see, comparable temp equals data root equals data max is equal temp. That's the very famous swap operation between 2 elements of an array. You need to have a temporary variable to do that. And then at the end, you're going to percolate down max in a recursive fashion because you may not be able to fix the percolate down by doing one swap. You may do it multiple times, as I showed you in the previous slides. The next operation is called extract max or extract root. Because I'm going to do implement a max heap using Java, I just need to do extract max. As you see, if the size is 0, we're going to throw an exception. You can call this a legal state exception. You can call it underflow exception, overflow exception, whatever type of exception you want to throw, that's fine. You cannot delete an element from an empty heap. That's why we have this condition first. Then, because it's a max heap, the maximum value would be at index 1. Because index 0 is empty, so index 1 would be the maximum. We're going to return RV at the end, but before returning it, we got to fix the max heap property. So we're going to do a percolate down on the root. So we basically say, let's swap the size, the element at the last cell of the array with the root. Then we're gonna set the element at index size equal to the root. That's how you swap the root and the last element. We're gonna subtract the size by 1, and then we're gonna percolate down the roots. Right? That's going to fix the maxi property after you remove the maximum and replace it by the last leaf or last node in the array. At the end, you're going to return the return value, which was the maximum. The next operation is going to be the preparation operation for insert operation. In order to do the insert operation, you need to first have a private method called percolate up. And I told you that's a sub procedure for insert operation. Percolate up is going to fix the maxi property when you want to insert an element at the lowest level. When you insert an element at the lowest level, it may not satisfy the maxi property, so you need to do percolate up to fix the maxi property, if you remember. I did that in the previous slides. So let's do percolate up in Java. If the element that you want to percolate up is already root, so that's it. You don't need to do anything else. That's the base case of my recursive implementation for percolate up. Otherwise, I need to find the parent, which would be the index of the current divided by 2. Instead of divided by 2, I could have done shift to the right by 1, but it's not so readable, so I skip that. Then I will compare the parent data with the current node. It should be greater because it's a maxi, but if it's not, if it's less, then you need to swap the current and the parent using these 3 lines, and then you need to continue the percolate up with the parent, because one swap may not fix the maxi property. You may need to do multiple times. Now that we have seen the Java implementation of percolate up, the insert will be extremely simple. You want to insert a certain value, let's say comparable value, into the heap. All you need to do is to check whether the length of the array is long enough to store that element. Here I said if it's not, if the size is equal to the length minus 1, that means you have a full array. Just throw an exception. But instead of doing that, I could have simply grow the size of the internal array stored in the max heap, which is basically the data array. I could have moved the data from the current array to the new long array, but I did it this way because I didn't want to complicate the implementation here. But growing the size is not a big deal. You just need to create an array with the length twice this current array, and then move the data from the current array to the new array. That's an extremely simple operation. I'll leave it for you to do it if you want to create a heap that has an infinite capacity, but this implementation has a finite capacity. It doesn't insert data into a completely full heap. After doing that, we're gonna do size plus plus. Then we're gonna set the size. We're gonna set the element at index size equal to value. This value is what you're gonna insert. That becomes the lowest and the rightmost leaf in the binary heap. That may not satisfy the maxi property, so you need to immediately call percolate up on the index size to assure the maxi property. That's pretty much all insert does. The constructors are already implemented before, so I'm gonna use the constructor of build heap I'm gonna use the constructor of binary heap to do the build heap operation. So if you want to do build heap if you want to build a heap using a sequence of elements stored in an array of comparables, all you need to do is to call the constructor of binary heap on that array, and it's going to do it for you. I remember I showed you how it is. I'm going to explain that more next. Then heap sort operation is quite simple after we have implemented the build heap operation and extract max operation. The first step of heap sort is to build a heap using the given array of comparables. The array is called values. So we use build heap to create a heap, create a binary heap, binary max heap. Then in a for loop, we're going to keep extracting the maximum. When we extract the maximum, we place it at the end, and this operation happens many, many times, causes a sort operation on the given array. And that's how you sort the whole array. I'm going to show you how this heap sort operates with a simple example in the next slides. Before I show you the details of heap sort, let's do a quick test on the code that we did. Let's have a main method, and in this main method I have created a binary heap with 10 as the capacity of the heap, and then I have inserted these elements into it: 5, 6, 50, 60, 15, and 16. After doing all these insert operations, the heap will have a size equal to 6 because I have inserted 6 elements in it. And then I start extracting the maximum using this while loop. The first thing that will be extracted would be 60 because that's the maximum value. So we will see 60 on the output. Then you will see 50, then you will see 16, then 15, then 6, then 5. That's what the outcome of this while loop will be. And then I have tested the heap sort operation. I have created an array of comparables with these values in it. Here I have -1, 5, 6, 2, 3, 1, 8, 4, and 0. As you see, it's not sorted. After I call the heap sort for it and then print the values of the array, what I will see is a sorted list. I will see -1 first, then I will see 0, then 1, then 2, then 3, then 4, then 5, then 6. And the last thing I will see would be 8, right? So that's how you can test your implementation of binary max heap and heap sort. All right, so let's look at an example of heap sort. Imagine you're given a list of n comparable objects in this order, as you see: 15, 10, 8, 30, 50, 16, and 20. I have placed them in a normal array, and what I'm going to do is I'm going to build a heap using this. If you remember my Java code, I had to do first pass this array into a constructor, a binary heap, to construct a heap. To do this, I need to do a bunch of percolate down operation. I call this a build heap from bottom to top. This is the very first step of heap sort. Let me show you how it looks like in this example. So if you make a binary heap using these elements stored in this array, what you get is this. And as you see, 20, 16, 50, and 30 are leaves. So we are not going to change these. We're going to assume these are basically 4 heaps by themselves. You have 4 separate heaps, each one with 1 node, right? One of them is 20, one of them is 16, one of them is 50, one of them is 30. Don't touch them. Let them be there, right? Then focus on the internal nodes first. Beginning with the last internal node, which is 8, you're going to try to see if that node 8 is placed in the right location. If it's not, we are going to fix the location of it by doing a percolate down operation on it. So as you see, 8 is not satisfying the max heap property because it's not greater than its 2 children, 16 and 20. So we're going to swap it with the maximum child the way we said it before for percolate down operation. So that's the very first heapify or percolate down operation that we're going to do. We're going to swap it with the maximum child, which is 20. After you do the swap operation, we get to this location. We get to this state. We're going to have 8 in this node, 20 in this node, and that's the end of percolating down or heapifying the element at index 3. Now we're going to move one step backward to index 2, and we try to heapify or percolate down this node. 10 is not greater than both of its children. The maximum child is 50. We're going to swap 10 and 50. And that's going to basically cause another percolate down operation. We're going to swap 10 and 50, and 50 becomes the parent, 10 and 30 become the two children. The final step of build heap is to percolate down the roots. I percolated down index 2, now I have to percolate down index 1, which is the root. To do that, I just need to compare 15 with the two children, 50 and 20. It is not greater than both of them, so we're going to swap 15 with 50, which is the maximum of the two children. That's going to be the third heapify operation. You're going to swap 50 and 15. The next step is to heapify, to compare 15 with its two children again. Again, 15 is not greater than the two children, so we need to have another swap in this third heapify operation. 15 should be swapped with its maximum child, which is 30. Now this, after this swap, now we have a perfect max heap, which is basically the final result of build heap operation on a given array. That's the first step of heap sort. After this, we're gonna start the second step, which is doing delete max or extract max or extract root operation n-1 times until everything gets sorted. As you see, this is the outcome of step 1, which was basically the sorted the max heap created using the given elements in the array. I created this max heap from bottom to top. As you saw, I skipped the root, the leaves first, and I made the heapify operation applied on this node first, then this node, then this node, and now it is a max heap. The next step is to begin step 2, which is going to be extracting max n-1 times. The first step would be to extract the current roots. So in order to extract it, you're gonna you remember the operation in the previous slides. You're gonna swap 50 and 8. 50 will be in the last cell of this array, and then you're gonna do a percolate down operation because you do extract min, so it's gonna you're going to do extract max, so it's going to change the max heap property. It wouldn't be a max heap, so you need to fix the binary heap, so you have to do a percolate down to fix it. Then after this step, you're going to extract 30 again, extract max again. The 30 will be placed here. Now 20 becomes the next maximum element, so 20 becomes the root after doing the percolate down. Then you have to do it again, extract max again. 20 will be here, now 16 is the root. Then do it again, 16 will be the next element, 50 will be the root. You see this red line that shows the border between the sorted subarray and unsorted subarray. So as long as this red line hasn't reached to the beginning of the array, we still have extract max to do until we get to the sorted list. And finally, to complete the heap sort operation, we need to do the remaining extract max operations. You're going to extract 15. Then you will have only 2 elements in the heap, and almost everything is sorted. Finally, you extract 10, and then you get the final sorted list. 8, 10, 15, 16, 20, 30, and 50 would be the elements stored in the sorted list. Now that we have seen the heap sort operation, let's find out its time and space complexity. The time complexity is going to be order of n log n, which is a subquadratic or quasi-linear sort operation, just like the merge sort or quick sort. As you see, it was made of two steps: build heap operation and repetitive extract max operation. The build heap operation takes you order of n. That's not very obvious. You need to calculate it in the following way. First, you need to heapify the lowest level because we had to build the heap from bottom to top. We had n over 2 squared different nodes, or this is like a approximation for measuring the number of elements in the lowest level. That lowest level max heap operation takes only 2 comparisons, so it's going to be n over 2 squared times 2. The next level has n over 2 cubed times 3, which is the number of comparisons. The next level we had n over 4 nodes, and each one takes 4 operation, all the way to the very first level, which has only 1 element, or n to the power of 2 to the power of h, where h is the log n, times h operations, or h comparisons for each heapify operation. The total would be the sum of all of these, which is going to be n sigma I from 2 to h, I over 2 to the power of I. This sigma can be simplified as n over h. I'm sorry, it can be simplified as a constant value, which is equal to 2, I guess. So this is going to be 2n, which is order of n. And that's the complexity analysis for the build heap operation, which is linear, surprisingly. The second step, which is repetitive max heap operation, takes you n log n. Why? Because the heapify operation takes order of log n, and you have n minus 1 operation, and times log n would be n log n. Therefore, the heap sort takes n for space 1 complexity plus n log n for step 2 complexity, which is going to be n log n overall. The space complexity of heap sorts would be order of 1 auxiliary space complexity, which means except the array that you have to keep the input, you don't need to use any other extra array to store elements. So the heap sort is called the in-place sorting algorithm, unlike merge sort, or similar to quicksort. We call that an in-place algorithm. In-place algorithm means the space complexity except the input, which we call it the auxiliary space complexity, should be order of 1. Finally, let's take a look at the way heap sort is compared with other sorting algorithms. As you see on the top, we have heap sort with the average time complexity n log n, best time complexity of n log n, worst time complexity of n log n, average space complexity of order of 1. This is the auxiliary space complexity, I should say, and the total space complexity of n. For the other sorting algorithms, the average time complexity cannot beat heap sort. Insertion and bubble sort are worse. Quick and merge are the same. Shell sort with Heap sequence, Heap increment sequence would be n to the power of 1.5. And selection sort is worse. It's n squared. If you compare the best time complexity, then heap sort is not the best. Bubble sort and insertion sort are shockingly better, because if you have an already sorted list, the insertion sort or bubble sort doesn't need to do anything. But for the heap sort, it's going to still take you n log n. If you compare the worst case scenarios, you can say heap sort along with merge sort are the best. Quick sort is not as good because heap sort worst case scenario would be n squared. The auxiliary space complexity for heap sort is the best. Merge sort is not the best, it's order of n. The quick sort, here I mentioned order of n because the book implementation was order of n, but you can do quick sort with order of 1 as well. So this can become better if you implement quick sort in a smarter way. That would be order of 1. And finally, the total space complexity will be order of n for all of the scenarios.